Okay, this week, we were just going to or today, we're going to review some HVAC drawings. This is a hospital, and what you're seeing here is ductwork going up to the roof. This would be the high pressure duct right here. They've chosen to use square duct instead of round. So this duct would be the SMACNA duct. This is classified probably as 4 to 10 inches. And the gauge and reinforcement would be such that would stand that kind of pressure. They've shown some kind of odd fittings here that may or may not get built like that. But this is ductwork going up to the rooftop unit, branching off, going to other areas, branching off to a VV box. This is what's called the high pressure duct right here, up to the VAV box. And the VAV box here is going to be a point of pressure change, and all this duct constructed downstream of the VAV box is considered low pressure. This looks like a typical patient room where you got a slot, diffuser along the perimeter, return grill here, supply grill here, another supply over here. Another supply duct going down to another floor. This looks like the return coming from the air handling unit going down another floor, branches off here, probably wraps around the building like this. All this return duct they would build as low pressure. Gauge and the reinforcement would be such that it's probably about 1/2 inch to 1 inch pressure. Straight fittings coming off of it, going to bath or to the rooms. Let's see the exhaust. Can't hardly see the floor plan. That's the exhaust right there. Picks up the toilet rooms here, toilet room there, toilet rooms in each patient room. That's considered low pressure duct. If it's connected to a fan, it could be part of an energy recovery unit, or you might be using air terminals on the exhaust even. Especially like in this OR right here, they might use an exhaust air terminal or return air terminal to balance the airflow to get a particular pressure relationship in the room. So instead of just a simple supplier terminal coming into the room, you may have a supplier terminal that comes to a diffuser. And an exhaust air terminal that comes over to and what they're trying to do there is they're measuring the air in each room or each air terminal through that cross flow device in the connection. And what we use, and most people use, is one single controller in this application. It's called a room pressurization controller. Very similar to the same TEC or terminal equipment controller that's on a duct, but it has 2 pressure transmitters that the high and low from these cross-flow temperatures are going back into the same controller. So what it does, it measures the supply and exhaust airflow, and through the programming, I either want a positive or negative pressure relationship. If it's an isolation room in a hospital, I would want a negative pressure relationship, and I would program, that to be 300, maybe that to be 350 or 400 CFM. In an OR, or a positive protective environment room, might be just the opposite. This is 400, this is 300. And the balance goes out the door or through another exhaust grill, or generally about out the door. So you could have, in this case, This is just an example of a system that we could use to balance pressures in a room. Nothing going right today.
Unless whatever that stuff is inside, all that water may be soon. People sit on the pedestrian.
It comes back up, I'll show you the operating room. This is a stretcher with a body. In an operating room, your clean environment or your sterile environment for air distribution purposes is right there. So my return is in a chase. So I've got a low return right here. And in the other corner, another chase. A low return right there. The idea is to supply some type of air diffusion where there might be slots that you're discharging air straight down like this, and the air flows like that. So I create a perimeter around that stretcher to create a sterile zone in that stretcher. There are also sealant diffusers that can do the same thing. What I don't like about sealant diffusers, and these are dumping type sealant diffusers, is that unless I've got a HEPA filter right here that cleans that air, I'm dumping air right on that wound, open wound. And what they've done, they've got some type of sterile diffuser shown around that bed and around the light fixtures. There's another thing you have to coordinate with. There's generally a light fixture that wraps that room all the way around. I guess they've got their sterile diffusers inside the light fixtures. And hopefully there's a filter right there, but of course you got HEPA filters or 90% filters in the unit, but ductwork's not 100% clean, not sterile. So one way is just to create a perimeter curtain around the room. Another way is to use a sterile type diffuser, and it creates a piston of airflow. For the slots to a curtain, when you have these type of diffusers, you've actually got airflow like that, and that creates a piston of airflow. And what happens is any contaminants are picked up and swirled around on the outside like this and into the return. No contaminants can get into that piston of airflow because it's at 50 to 150 feet per minute discharge. So that's a typical air distribution system for an operating room. I think we're showing the light fixtures, maybe right there. What they're doing is similar to that piston type distribution system. That's an OR, and that's some of the critical things you have to know about an OR. In a hospital isolation room, stretcher. It's generally right there. And in an isolation room, we want to isolate the other folks around here. So we don't want a return over here to drag air back to the nurse coming in the door. In an isolation room, you want that return and supply diffuser here so that you're creating the airflow pattern across the patient and out the room to protect people coming in the room. Just the opposite in a protective isolation. You don't see a lot of protective isolation rooms. Those are generally transplant rooms, burn rooms, some children's and UMS, that's probably the majority of those type of rooms. In a protective isolation room, you want to protect the patient. So in a protective isolation room, air is going out. In a negative isolation room or typical isolation room that you'd see in a hospital where you're trying to protect this is a contagious patient, air is going in. And in a protective isolation room, you do just the opposite. Put the supply here over the patient, protect him, and the return goes into the toilet or into an anteroom out here or just some exhaust out here. So those are kind of critical air distribution methods for hospitals that you might want to take note of if you see it. Damn. Gotta get another pointer. Another thing I've got is mechanical room. Show you some piping layouts, how we've been talking about them. The other thing I was going to talk about in the air distribution, you got supply from an air handling unit, ductwork comes out, goes to a VAV terminal, goes to a diffuser. Turn comes back. Same method as in that pipe system. You get a certain velocity and a certain pressure drop in this ductwork system. So as I was calculating the pressure drop, I would calculate the pressure drop for this string of certain CFM, pressure drop in that fitting, which is a straight through T, and pressure drop this duct based on the CFM fittings. The VAV terminal has a certain minimum pressure drop. Generally it has a reheat coil, which is going to be your typical pressure drop, and then whatever it takes to get out to the diffuser. So in round numbers, you know, most people allow about 1 inch for the VAV box in the downstream, maybe a little less. In a typical VAV application similar to the one we were looking at, you've probably got, with all these things, probably somewhere in the neighborhood of 2 to 2.5 inches pressure drop in the duct. And in the air handling unit, you got filters, you got coils, whether it might be 1 or 2 coils. You got pre-filters that have a preheat coil, cooling coil, maybe a diffuser on the fan, and then some plenum losses. So pre-filter, and then you might have a final filter. So pre-filter generally is going to be in the range of 1/4 of an inch, but you want to figure it dirty. So you might figure it at 7.5 inches. And a preheat coil, generally about 1/4 of an inch for a 2-row coil. A cooling coil is generally about 1 inch. Diffuser, about 1/4 of an inch. Plenum losses for the whole air handling unit probably don't add up to more than 1/4 of an inch. Final filter, generally about 7.5, but you want to figure it dirty. Final filters don't get, if you maintain your pre-filters, don't get quite as dirty as pre-filters do. You might go to 1 inch, you might go to 1.25 inches. That's a good thing about a drive on an air handling unit. Because when you initially start up, you're down here, and you're eventually going to load up to there. So when you start the unit up clean, hopefully you're not at 100%. So in ratios, like we were talking about between piping and chillers, so this adds up to half, 1, 1.5, 1 3/4, 2, 3 1/4 inches for the air handling unit, and 2, 2.5 inches, so probably about 3 inches for the ductwork. And that's pretty typical, pretty typical ratio. So again, if I'm concerned about the ductwork and the fittings, that's not the entire pressure drop. You know, if I increase this 20%, that just gets me up to 3.6 inches. And so my total is going to be somewhere around 7, 6 1/4. You know, the engineer is going to put some safety factor on there, probably even selected at 7 inches for some safety factor, including this safety factor right here. That's not actually a safety factor, that's a fairly known system. So it calculates very similar. You have fitting losses, you got straight line of pipe fitting losses, just like pipe. The elbows are so many equivalent feet, just like we figured in an elbow in a piping system. Diffusers have a certain loss, and we didn't even add in the return to this. Generally, in the low pressure side, I probably want to max that out at somewhere around 7.5 inches, 3/4 of an inch, half to 3/4 of an inch. So turned up 7.5. And my balancing for this is strictly at these dampers right here. It's the only place I've got to balance. On the supply side, it's just like when I talked about a correctly sized control valve. The supply side is self-balancing. These are called pressure independent. Pressure independent boxes, meaning that no matter what the pressure is here, and so this is going to vary when all these boxes are closed, this pressure might be at 0 inches because there's no airflow, there's no friction in the duct. They're never going to close, so this might range from 1/2 inch up to 2.5 inches in pressure. These boxes don't really care what the pressure is because I'm at this cross flow sensor right here, I'm measuring velocity and pressure and converting it to CFM. So I always know what CFM is as long as I've got at least enough pressure to measure it. So this is called a pressure independent system. This is not pressure independent. It varies, but it varies proportionally. So theoretically, once I balance these grills, I get the same proportion as the airflow goes up and down the supply. All that's looking. Load up the mechanical one. since you're the novice in here, you got any questions?
No, I'm just,
Now, I can't get this screen to come back. We're gonna look at the mechanical room and see how a pretty decent mechanical room is laid out, clearances, equipment, how the various equipment looks like we've been talking about. I don't think it's gonna come.
You got a set of plans that shows a mechanical room that's got enough room in
Yeah, let me go get a drawing, we'll just circle around.
I got a hammer out in the truck, we
Yeah.
use it one thing.